Welcome to This Explainer. If you've ever felt completely bogged down by calculating point after point just to draw a simple curve, well, you are definitely in the right place. Today, we're going to completely master graph transformations. Because honestly, whether you're modeling financial data, mapping the trajectory of a physics simulation, or, programming a jump in a video game, you really need to know how to stretch, slide, and flip mathematical shapes without all that tedious coordinate plotting. So let's just dive right in. Here's a quick look at our roadmap for today. We'll start by meeting your parent function, then move into shifting graphs up and down, and horizontal shifts left and right. After that, we're flipping and stretching the shape, tackling step-by-step multiple transformations, and finally wrapping up with the ultimate transformation cheat sheet. All right, part one, meet your parent function. So our primary visual protagonist for this explainer is going to be the square function, f of x equals x squared. Just picture it as this perfectly symmetrical, simple U shape resting right at the origin of your graph, just perfectly balanced at 0. And because it rests right at 0 and has this beautiful symmetrical curve, it's basically the perfect test dummy. Seriously, anytime we shift or stretch it, the changes are going to be instantly obvious. We're going to use this reliable little curve as our baseline canvas to test all of our transformation rules today. But before we start messing with our baseline canvas, we need to understand exactly what kind of move we're making. First up, we have rigid transformations. By definition, a rigid transformation means the shape and size of the parent function remain exactly the same. The graph is only shifted or reflected. Think of it exactly like sliding a solid wooden puzzle piece across the table. Its core shape never distorts, right? It just relocates to an entirely new neighborhood on your grid. Moving right along to section 2, shifting graphs up and down. Okay, so when we apply a vertical shift up, which means adding a constant k entirely outside our function, every single y value simply increases by that exact amount. The whole U shape just moves higher. Conversely, subtracting k completely outside the function acts as a vertical shift down, where every y value decreases by k. The absolute crucial takeaway here is that changes entirely outside the function affect the graph vertically, and they behave exactly as your logical intuition would expect. Plus literally means up, minus means down. Like, if a company's baseline profits go up a flat $10,000 across the board, the whole curve just shifts straight up. Super easy, right? But hang on a second. What if we change the inside of the function? As we're about to see, the x-axis behaves in a completely counterintuitive way. Subtracting actually moves us to the right. Wait, why is that? Which brings us nicely to section 3, horizontal shifts left and right.
All right, here is where things get a little tricky. When we subtract a number h inside the parentheses, y equals f of x minus h, it actually shifts the entire graph to the right. Every single x-coordinate increases. And conversely, adding h inside shifts the graph left. Think of it kind of like a delay. If you subtract from the input, the function literally has to wait longer, or, go further to the right down the number line, just to hit the exact same output it used to hit at 0. It's playing catch-up. If you take away just one overarching rule today, please let it be this. Inside is opposite. Manipulating the inside of the function does the exact reverse of what your brain expects it to do.
Okay, section 4, flipping and stretching the shape. Let's talk about reflections. A negative sign placed completely outside the function, y equals negative f of x, flips the graph vertically across the x-axis. It effectively multiplies every y value by -1. Imagine a mountain instantly turning into a valley. But slip that negative sign inside the parentheses, y equals f of negative x, and it flips the shape horizontally across the y-axis. Once again, notice the pattern? Outside impacts y, inside impacts x. Now we're graduating to non-rigid transformations. This means the mathematical shape of the parent function actually changes. Imagine swapping out our solid wooden puzzle piece for a rubber band. We're no longer just relocating it, we're literally stretching and squishing the graph itself, making it taller, shorter, wider, or narrower. So multiplying by a constant entirely outside the function stretches the y values directly. A multiplier of 2 makes it twice as tall, basically pulling our rubber band straight up. But multiplying inside uses the reciprocal of that coefficient. So putting a 2 inside the parentheses actually compresses the x values by a half, squeezing it inward. Why? Well, because the function is reaching its normal outputs twice as fast. It's exactly like fast-forwarding a video. It compresses the time or space needed to finish the action. Once again, manipulating the inside does the exact opposite of our intuition. Section 5, step-by-step multiple transformations. Watch how reading the equation from the inside out gives us this logical, step-by-step recipe. Let's say we want to graph y equals -2 times x minus 3 squared plus 1. Step 1, the base. Start with the plain U shape, good old x squared. Step 2, go inside the parentheses. The -3 tells us to shift right 3. Step 3, move just outside. The 2 stretches it vertically, making it twice as tall. Step 4, the negative sign reflects it upside down over the x-axis. And finally, step 5, the +1 at the very end shifts our entirely new shape up 1 unit. Beautiful, right? We just graphed a highly complex function purely by looking at its pieces, without plugging in a single raw coordinate.
Finally, Section 6, the ultimate transformation cheat sheet.
Here is the golden rule realized, basically a master key for visual algebra that you can take anywhere. Outside alters the y exactly as expected. Adding goes up, subtracting goes down, and multiplying stretches. Meanwhile, inside alters the x in wonderfully counterintuitive ways. Adding moves left, subtracting moves right, and multiplying compresses. This right here is your ultimate cheat sheet for any function going forward. It is incredibly liberating to look at a massive algebraic equation and instantly know its exact shape just by spotting these telltale signs.
So, here is my parting thought for you today. Now that you know outside alters y normally and inside alters x backward, what incredibly complex systems can you easily visualize next? Whether you're mapping the trajectory of a rocket, creating a 3D animation, or just tackling your next math challenge, ask yourself, how does this simple inside versus outside trick change the way you see the hidden code of the world around us? Keep that curiosity alive, and I'll catch you on the next explainer.